but it should be clear. So the problem we want to solve is, we have any number, for example, 5, and we want to exponentiate to another number. For example, I don't know, we could say 18. So I'm going to write it like this. So 5 to the 18. Like, for example, we want to compute 5 to the 18. Now, this is something that seems like how would you do this? Like, exponentiation is defined as repeated multiplication for starters. So this is like, I do 5 times 5 times 5 times 5, and I do this. I have to multiply 5 by itself a total of 18 times, and then I have my answer. So like here I can simply like I can use Python. I can do like print 5 to the 18. In Python, the exponentiation is a double asterisk, and I get this, big number. So this is like what you, study like elementary, middle school. I don't remember, and this like seems okay. But the problem is that this method is really bad when this exponent is really huge. Like, it doesn't scale at all very well. And we can see that if we just like, I don't know, we write something like Python function, slow exp, I take like my base and I take my exponent. And the result is going to be like, first I'm going to start with 1, because that's like if you exponentiate something, you're going to get at least 1. Because like 5 to the 0 is 1. And then what do I do? Well, I do a for loop for e in range from like, let's say 1 to e, which is my exponent. I do result equal result times the base. So I multiply the base by itself this many times, and then I simply return result. This is like an implementation of our computation. If we print this, like here I'm gonna try to execute this script. So let's like hire up the exponent. This is still works, but of course in in RSA we have really big exponents. So like we can go all in, let's say. Now we can wait like until we die, and this is probably not gonna stop because it's implemented like not in efficient way. So like the complexity here, we feel it, because the problem is that this kind of complexity, like I'm not gonna do like a theoretical study on the complexity of this algorithm, but essentially this exponential complexity. It means that the longer the number is, the way it grows, the computation time it takes, it grows exponentially with respect to the size of the number. So this is bad. But of course, we have to do this kind of problem. We have to solve this problem because in RSA, we actually have to exponentiate to a much higher number than this. This is actually like a small number. And we want to do it in a matter of seconds, because each time you make a necessary connection, a TLS connection, you have to solve this problem a lot of times. The server has to do it for each client. So how do we do this? Now, the idea here is to rely, of course, on algorithmic theory. And essentially, the idea is, okay, I will rewrite the exponent in a different way. Because here I wrote it as 18, and then I just did 5 times 5, 5 times 5. But what I'm going to do now is I'm going to take the binary representation of 18, which like I can compute it, like I don't remember which is it. So like it should be this thing. So like 18 in base 2 is equal to like this thing, because it's like this is 2, and then this is 16. This is 2 to the 1 plus 2 to the 4. That's like 2 plus 16, and that's 18. It's the same thing. So I can rewrite 18, but in powers of 2, using the binary representation. And this is going to be really, really important. So now I have my 5 to the 18. I can rewrite this, because after all, I've rewritten 18 as 2 plus 16. So this is going to be 2 to the 5 to the 2 plus 16. Nothing has changed mathematically. Now I can use the property of powers. So if I have like the base to the a plus b, I can simply split this kind of thing, and I can do 2 to the 5 to the 2 times 5 to the 16. So this is essentially the same sort of computation. And the idea now is to realize that instead of like thinking about this in terms of 18 multiplications, I've split it into 2. Of course, I still have to compute those 2. They don't come for free. But the idea is that now everything is going to be like a power of 2, meaning that what I do computationally is I just compute the following powers. I compute like 5 to the 0 is 1. Let's count it. Then I compute 5 to the 2, which is 25. And I'm not going to compute 5 to the 3. I skip this. And I compute 5 to the 4, which is, I don't know, it's like I can use Python shell. No. Which is 6 to 5. And I'm not going to do 5 to the 5th, 5 to the 6th. I'm going to do to the 8th, which is the next power of 2. And then I do this, I get this number. Of course, this number grows very fast because the exponent is growing very fast. The next number is going to be to the 16, the next power of 2. I compute this, so 16. I have this huge number. Now, the thing is, at this point, I can still keep going, right? So I can do the next power of 2. What is the next power of 2? It will be 5 to the 32. But, I mean, my problem was to compute 5 to the 18. There is no no point to compute this power. It is just too big. I went over the exponent I needed. So this I can stop. I don't even need to compute this. I can stop. So now essentially I have these different powers, and I just need 2 of them actually, not all of them. I don't need 2 to the 4, for example. Yeah, actually, no, I need 2 to the 4. Yeah, I need 5 to the 4. Sorry, I need this one. I need essentially no. What am I saying? I need 5 to the 16. So I need 5 to the 2, which is this one, 25. And then this 5 to the 16, which is the last one I computed, which is this one. I do this computation, like this 25 times this other number, and I get back my result. And if we now like sum all the multiplication that we did in this thing, essentially what we did is this is 1, so we have 1 multiplication. We have this other, which is like a second multiplication. Now the trick is to compute 5 to the 4. I can reuse the previous value because 5 to the 4 is 5 to the 2 times 5 to the 2. I exploit this fact. So essentially, I just do 1 multiplication and I compute 5 to the 4. Then I can use the same idea to compute 5 to the 8, which is 5 to the 4 times 5 to the 4, which I previously computed. This is like 5 to the 1 times 5 to the 1. And at the end, I have 5 to the 16. Okay, but I know 5 to the 8, so I do 5 to the 8 times 5 to the 8. So now, essentially, if I count all the multiplication that I do, like from 0, I have like 1, 2, 3, 4. And then this is like to compute all the ingredients that I need. And then I combine only the numbers that I care. So that's 1 more. So it's like 4, 1 more 5. I did the 5 multiplication instead of 18. And this this trade-off, which is like this 13 less multiplication that I did, actually scales exponentially. So like when I have super huge numbers, what I do is like I'm much faster. So the idea to recap everything and to like start from scratch. The idea is that anytime you have to, suppose now you have to do like this 13 to 137. It's pretty huge, okay? So the first thing you do, like in the algorithm, this is like the algorithm for humans. Then we will see a better way to implement it for machines, which is more confusing. I think this is more straightforward because it is more linear. The first step is compute binary representation of exponent. So 1337, you compute the binary representation of 1337, which is this thing. Because we will split it into parts. This first is going to be like 1 plus 2, 4, 8, 8, that's 16, 16, that's 32, 64, 128, 256, 156, 1024. Let's see if this actually works. If I have not made any mistake, print, get 1337. So we have splitted our exponent in a bunch of powers of 2. And this is the first step. The second step is compute all, let's call them ingredients of the form 13 to the, like, I would say, power of 2. The theoretical form is like 2 to the I. 13 to the 2 to the I. So all the powers where the power is like itself a power of 2. So in this case, it is like 13 to the 1, which is just 13. 13 to the 2, which is like 13 times 13. So we compute it. So we do 13 times 13. That's 169. 13 to the 4, which is 13 to the 2 times 13 to the 2, which is 164 times 164. Print this. Then we do 13 to the 8, which is 13 to the 4 times 13 to the 4. We just repeat the same idea. Print. Then we do 13 to the 16, 13 to the 8 times 13 to the 8. Times this. So it's like print this times itself. I mean, of course, in the midterm, the number is going to be really small. So this is just to get an idea. It's going to be much simpler when you actually have to do it by hand. Because otherwise, even this like small multiplication would be like tough. So 32, so 13 to the 16 times 13 to the 16. I mean, here the numbers are getting pretty big, but we don't care. So we do this, it's going to be huge. 64. So we still need, like, essentially we need all the powers until the highest. In this case, it's going to be like to the 64. Then we need to the 256. So here we will still need 128, 256, 502, and 1024. So we need all of them, and we cannot skip any in this step because to compute the next one, we need the previous one. So there's like no easy ways. Now this is kind of boring, so maybe I don't continue, but you can continue if you really like this. Not sure how cool it is, but at the end, we will have a bunch of powers of 13. We will have all the numbers for this. And finally, put together the various ingredients. depending on the binary representation of the exponent. So, I mean, like an answer could be, where do I stop with this, like with this computation? And you stop once you reached the highest power in the representation of your exponent. So in this case, the highest power is the highest like value is 1024. You don't go further, because if you go further, it's gonna be, you don't need that. You already exceeded the number you want to represent. At this point, you have all these value that you computed. They are not that much. I mean, the numbers are huge, but if you just count them, they are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They are like 10 multiplication you did. And remember now that we are elevating to the 1337, so it's a little bit huge. So now, once you have all these ingredients, how do you put them together? Well, I mean, your objective, I mean, our objective was to compute 13 to the 1327. Okay, but then we said, okay, but 13 to the 1327 is simply 13 to the 1 plus 8 plus 16. So this is the like this is the main idea. Oh, shit. This is the main idea. Like, why do we write the binary representation of the exponent? So that we can rewrite the exponentiation, and then you just do the like property of powers. This is 13 times 13 to the 8 times 13 to the 16. Like here I put some parentheses. Times 13 to the 32 times 13 to the 256 times 13 to the 1024. All of these numbers, you already have them, because, for example, 13 to the 1 is 13, 13 to the 8 is this order that we computed previously. So we have all these ingredients. We can keep substituting them until we have our numbers. And even in this case, the number of multiplication that we do is no more than 10. At most, it will be 10, because like at most, we will need every ingredient. Each ingredient appears only once, so we could have at most other 10 ingredients here. So you do this multiplication and you arrive at your result with like, let's say 20 multiplication instead of 1337. And this is actually faster in the RSA, because the example I showed here was done in traditional arithmetic. The thing is that when we work with modular arithmetic, there is like something that helps us. And the thing is that the size of the numbers, we reduce it after every multiplication. So like this is like traditional. So this is traditional arithmetic. In modular, the same idea applies. But the thing is that after you do each multiplication, you have like 3 numbers. Let's say you have an x, a y, and an n, and you want to compute, like we want to compute x to the y mod n. So this is what we are interested in. The base is x, the exponent is y, and the modulus is n. The same idea applies, same idea as before, but now you reduce modulo n after each multiplication. Like, let's say, like an easy example. So all of these like notes of the example. I show some example. Like for example, let's take x to be 5, y to be 37, and n is 13. So how will we do it? First, write binary representation of 37. So 37 is gonna be like into the pin 37 in binary, gonna be this thing. Is true. Base 2, because that's equal to 1. So this is the first. 2, 4. So we have to add 4. 8, 16, and 32. So that's 37. Okay, so we write the representation. Compute all powers of x needed. And the powers of x are, like x is 5. So we do 5 to the 1, that's 5. But now we have to remember the modulo. So we have to 5 to the 1 mod n, mod 13. So that's 5 mod 13, it is just 5. This is the first one. The second one is 5 to the 2 mod 13. So here we get 25 mod 13. And now we have to reduce. Because like if 25 is higher than 13, we have to reduce. I'm going to reduce it here. We do. Here I do print 25 modulus 13, which is 12. Then I do 2 to the 6 mod 13, 2 to the 5 to the 4. So I do it 12 times 12, because it's the previous one times itself. So that's going to be like what? 12 times 12 is 124 mod 13. You do 124 mod 13. You do 1, you get 1. Then you do 5 to the 8 mod 13. Now this is easy, because if the previous was 1, you do 1 times 1 mod 13. That's 1 again. Now we do 5 to the 16. Same thing, it's 1 times 1 times 1. And then, do we stop or do we go one further? Do we stop here or do we go one more? Yeah, because the highest power of the base is 32. So we need that. And we stop there because there are no higher powers. So this is 32, it's the same, it's always 1. And then finally, we put everything together and we get, okay, 5 to the 37 mod 13, that's equal to, first I write the exponent as a sum of powers of 2. I remember the modulus. Then I split the powers, the numbers in exponent. I do, and here I can also do like this. I can put the modulus within the operation, so to reduce further the cost of the multiplication, because modulus can be put inside. So this is the thing. And now I can use all the ingredients I've computed. So 5 to the 1 mod 13, that's 5. 5 to the 4 mod 13, that's like 1. And 5, and that's also like 1. So at the end, we get 5 as a result. And here we have another, everything has to be mod 13, is 5. And we can check this, like, we can check it, we do 5, 37, mod 13, and that's 5. This is essentially the main idea of this multiplication is you write the binary representation, you compute all the powers you need, and then you combine the powers you need. It is just like a different way to express the computation, which is much more efficiently. Also because, doing things with power of 2 in general is much more efficient because the architectures of our computers. So this is like the way I think humans can understand it easily. There is a way to implement it though, because we have to, like in our test, we have to compute this exponent. We have to do this kind of computation. I mean, I guess here we could put, like we could change this so exp to be x and y. So like the base is x and the exponent is y, and then we introduce like a modulo. So we do this operation and then we reduce modulo n. So it's the same as before, but now after each multiplication, we are reducing modulo n. And if I do this kind of thing, so here I guess I need to put the modulo. Let's say modulo 13. Let's say like this works. Okay, it still doesn't work, even if I reduce each computation modulo 13. The problem is not the size of each number, it is how many times you have to do it. So we are still not happy with our slow exponentiation. So we would implement like a better alternatives. And to implement it, there is like the approach I showed you was like very explicit. First you write the binary representation, then you write the exponent you need, and then like this. The way we will implement it in like the computer is going to be a bit more implicit in the sense that we will not write the binary. You have a question?
Excuse me, according to RSS formula, n equal to p multiplied to q. P and q should be prime number. So prime number multiplied them is not prime number. So you wrote n plus 13 prime number.
Yeah, but like this thing, I'm not sure how computationally it changes, but like here I could put anything, it wouldn't work regardless. Like regardless of the algebraic structure of the group, like the problem here is literally how many times you do the exponentiation, like how many multiplication you do. And they are so huge that regardless how you reduce them, you can reduce them modulo a composite number or a prime number. It's still going to be really slow because you have to do it so many times. That's really the huge problem. What we are doing here is reducing the number of multiplication to a really small number so that we can like exponentiate huge numbers to huge exponents without doing lots of multiplication. So we have to be like smart about that. So yeah, in RSA technically it's a composite number, the modulo, but in this case we don't really care about that right now. We will care in the other algorithm, which will be important. So the way we will implement it follows the following idea. So as we said, if I have like x to the y, I can write this as like, suppose that I take my exponent and I divide it by 2. So suppose for now that the exponent is even, so I don't lose anything. So the idea is that doing x to the y is like going and doing x to the y over 2 times x to the y divided by 2. So this is like mathematically correct if y is even, of course. It's like saying I have 4 divided by 2 is 2, means that 5 to the 4 is 5 to the 2 times 5 to the 2. This is like the thing if it is even. If it is odd, instead, what happens is that, for example, if I have a 5, so when I do 5 divided by 2, of course, I have to do the integer division, which means like in Python, it's like double slash. No, this is not Python, this is bash. So in Python, it's the double slash. I get 2. Like technically, it's like 2.5. I floor it, I take to the lowest integer. So like that's 2. So that's 2. Which means that the previous trick does not work exactly, because now if I like do, I don't know, 2 to the 5, that's not equal to 2 to the 5 divided by 2 times 5 divided by 2, because that would be 2 to the 2 times 2 to the 2, which is 2 to the 4. Every time the exponent is odd, I miss 1 time the base. I miss like 1 on the exponent. So it means that mathematically, so like if y is even, then we have this formula. Otherwise, if y is odd, then what we have is that x to the y is equal to x to the y. Here I put the double slash to say that it is an integer division. So I take the lowest, and then I have to add a little extra x to make things like work out. And so essentially the algorithm will use this kind of more recursive approach. The idea is the same. We are using the binary representation, but it is more like implicit in the recursive definition. This is more like a mathematically formula that works out. But in the previous, formulation, we could see why this is more efficient. So like to implement it, we essentially use this formula, because what we do is, so I'm going to write here. test. We do a fast exp, it's yn. So now this is going to be recursive. So like when we write recursive algorithm, we define the like base step, the one we know how to solve immediately. In the case for exponentiation, it is when the exponent is at 0. Because if I have anything to the 0, that's equal to 1 automatically. So what I do is, if y is equal to 0, here below, I do okay. In this case, it's 1. I immediately know how to answer. Otherwise, I know that y is greater than 0. Of course, here we assume y is greater than 0. Like we assume that everything is greater than 0, actually. So this is our base assumption. So if y is not 0, it's something greater. So what do? Well, we compute like an intermediate result, which we call like intermediate value, by calling the fast exponentiation function with the same base, but now the exponent is going to be y divided by 2. So it's going to be halved. It's like this is following this mathematical formulation. If we assume that we know x to the y over 2, then we can combine it to obtain x to the y. And so what we do is essentially we compute this intermediate value, and then we return something that depends whether the exponent is even or odd. Because if it is even, then we are good. If it is odd, we have to add that little extra. So we do like if y modulus 2 is equal to 0, meaning if y is even, we return the intermediate value multiplied by itself. Otherwise, if y is odd, we return the same thing, but we have to put 1 time the base, the x. We don't put the intermediate value again, we put the base, because it is this uppercase, this x to the y when y is odd. We split it into 2 equal, and then we multiply it again. And this is why this algorithm is called like the square and multiply, because we are squaring if we have an even case, but then sometimes we have to multiply if we have an odd case. And of course, the exponent changes every time we do this recursive call. So we can test our algorithm. We can test this thing. Maybe this is not. I have written a code. Let's check my other code, because I have already written this. I want to make mistakes. So let's say the square multiply. It asks for x, y, and n. Oh yes, there's something that we forgot to do in this other implementation. So let's try with this. Okay, so this is like you can find this code in the resource of the lecture. So you use this script by saying you call it Python. It doesn't require any libraries. And it says, look, I need 3 values, the base, the exponent, and the modulus. Then I put like, I put 5 as the base, this huge number as the exponent, and 15 as the modulus. And like it answered like in a matter really of seconds. Now, this other one that we implemented today was not working. Like if I do test.py, it's not working because in this implementation, of course, I forgot to reduce with the modulo. So there's no modulo reduction. So here, every time we do this, we have to do modulo n. We have to reduce everything modulo n. So if we reduce this modulo n, even this should work now. And it is 5. And it's pretty fast. I mean, we can probably put a little more digits for fun. And like it scales pretty well. And I mean, these numbers are really not that big. My laptop is not really that efficient. And this means that this algorithm is really like pretty cool. because it allows to do like this kind of stuff. So this is the first algorithm, and I mean so there are two ways to approach it, as we have seen. This thing is a more like a mathematical declarative approach. I mean, this formula is simply true. You can probably see it. It doesn't maybe tell you immediately why it is much faster. This other formulation, which is a bit more like complex in the terms of steps, things, I think that it allows you to see that this thing is so much faster because we are doing less multiplications. Because essentially, we are abusing the fact that we can write any number as a sum of powers of 2. But of course, the number could be big, but the number of powers of 2 that go in that number, they are not that big. I mean, it is the difference between the value of a number and the amount of digits we need to like memorize that number. I mean, if you think about that, like 1337, it's like, if you think about the number in terms of like amount of, I don't know, things, amount of 100, 300, like 1337 things, there are a lot, but this number is pretty small to write out. So what we did is like we use the notation efficiently. So this is the first algorithm, and I mean, you can simply do these 3 steps, and you get your answer, or you can also use this formula in the test. And yeah, to use this formula, you just need to divide the exponent, and then you go backwards and you compute these things. This is the first. The second, so this is like first algorithm. Put everything here. I mean, there are nodes written better than this. This is just to teach. The second algorithm, so this is the first, and here I've seen some examples, and you can also see some exercise. You can simply just repeat the same thing. I mean, as I said, in the midterm, there will be smaller numbers, so it's going to be really fast, actually. You just need to know to have understood the algorithm. The second algorithm that we'll see instead has to do with modular inverses, and it's a little bit, I think, more annoying. Because the idea is that in RSA, as we said here, so when we discussed RSA, we showed the computation to compute the key. And it was like, okay, we have 2 primes, we multiply them, we have an n, a value n. Then we choose an exponent t such that it is coprime with phi of n, so they share no common factors, and this is really important. And now we want to compute d, and I said that d is computed as the modular inverse of e modulo phi of n. So the question is, how do we compute the inverses modulo? So modular inversion. I mean, this is essentially division in a modular field, division in modular groups, division in modular groups. So for example, we have, let's say that we have like 2 like small primes, I don't know, 3 and 7, maybe, okay, 7 and 11. So this is a small n, so that's 77. And then, so this means that phi of n is like, phi of n is 6 times 10, so that's 60. And then we get an e, which has to be coprime with 60. Okay, 60 is like 2 times 3 times 2 times 5. So 2 to the 2 times 3 times 5. So for example, E7 shares no factors with 60. It means it is a good candidate for our exponent. I mean, now if you have a number, for example, I don't know, 13, you can compute m to the e mod n. We can compute this exponentiation using the algorithm that I showed before, but we will not do that now. What we're interested in is, okay, how do we compute the private key d of this configuration with these parameters? And the idea is with modular inverse. I mean, the key d has to satisfy the equation that d is equal to e to the minus 1 mod phi of n. Now, when we say that something is equal to something else to the minus 1, this is like an algebraic notation to mean that when we do d times e, we want 1. We want to obtain the neutral element for multiplication, and this has to happen modulo phi of n. So we are looking for a number, d, which when multiplied with e gives us 1. So we look for d such that when multiplied with e gives us 1 modulo phi of n. So now, this kind of thing can be rewritten because this, what does this mean? It means essentially that when we take d times c and we divide it by phi of n, we get a remainder of 1. So it means that d times, it means that phi, d times c is equal to phi of n times a quotient plus a remainder of 1. So we have this thing that we want to divide. This is the number we are dividing with. We get a quotient and we get a remainder. Another way of putting this all together is saying d times c minus phi of n times q is equal to 1. So you have this sort of combination that equals to 1. Now, the algorithm that we will see, it gives us, so the extended Euclidean algorithm gives us a way to compute x and y, such like, okay, let's start from the Euclidean algorithm itself. Like, okay, Euclidean algorithm. You have two numbers. So like you have a and b. And you want to compute, we want the greatest common divisor. Greatest common divisor between a and b. So the GCD, which is the number, the highest number that divides both of them. For example, if I have 10 and 25, the GCD, how can I compute it? Well, one way is saying, okay, for example, 10 is equal to 2 times 5. 25 is equal to 5 times 5. Now, a number that divides both of those is certainly 5, because 5 divides 10 and 25. Is there a larger number that divides both 10 and 25? And the answer is no, because any large number does not divide one of them. So the GCD of 10 and 25 is like 5. So this is pretty basic. But the idea is, once again, how do we compute this efficiently? Because, of course, we can factorize the numbers and extract the highest common divisor from the factorization. But factorizing is inefficient. We don't want to do that. So we want an efficient way to do this. And the Euclidean algorithm exploits an interesting fact that the GCD of A and B is equal to the GCD of B and A modulo B. We can essentially use this kind of formula, equation, theorem, and the interesting idea is that if A is greater than B, when we do this swapping with like the first argument becomes B and the second becomes A modulus B, we are reducing the numbers. So the numbers are smaller. One of them gets smaller until we reach like with the case when one of them is 0. And at that point we are done. Like I think that here, these notes I show an example with like 60 and 10. So here I'm like the GCD between 60 and 10. So you have GCD 60 and 10. So you use the formula. This is the GCD of 10 and 60 mod 10. Now 60 mod 10 is simply 0. So that's the GCD between 10 and 0. And if you have the GCD between any number and 0, it's going to be the other number. Because like everything divides 0, so the highest number that divides both of them is exactly the other one. So essentially you do this, And the algorithm that implements this idea literally simply execute this step. So like, I think that I have it here, the code, the basic, the standard GCD, the standard Euclidean. So you have like A and B. You check. If B is 0, you just return A. Otherwise, you return a recursive call, but with the swap. Instead of having A and B, you have B and A modulus B. And this gives you like the GCD. You can test it with essentially you do this. So modular code, and here you do like standard. You put two numbers like 6 and 10, and it gives you the value 10. And you can use these scripts. You can download them and execute them. Also to check if you actually understood the algorithm, you can try with some numbers and you can test if they give you the same answer that you got. So for example, the GCD between 1, 2, 3, 7 and 10 is 1 because they have no common factor. So if the GCD is 1, it means they share no factor, only 1, which is the basic factor that every number shares. So this is the standard, but the standard doesn't give us what we want. To get what we want, we need to essentially, we want a different thing. And we want based on the following result. For example, so this is a really efficient way to compute the GCD. The extended Euclidean algorithm does not compute only the GCD. So given A and B, you give me two numbers. Thanks to the extended Euclidean algorithm, we find x and y such that, so we find two numbers such that A times x plus B times y, A times x plus B times y is equal to the GCD between A and B. So we want this kind of relationship. And this can always be found. There is an algorithm that always finds this kind of relationship. And essentially, like we give an MA, okay, like for example, I give like numerical example. For example, we have A, so A is 137, B is like 175. So how do we go about finding this kind of identity? And the idea is, first, like this process is a little bit like one has to be careful with the computations, but essentially you start with your numbers, A and B. First, you compute the division of A divided by B. So for example, in this case, I have 1237, and I get 1237 divided by B. That's going to be 175 times a quotient plus a remainder. Because when I divide 1237 by 175, I'm computing a quotient plus a remainder, and the remainder, of course, is to be less than 175. Now, in this case, I don't even remember this thing, but we can simply compute them as follows. So the quotient is 7 in this case, and the remainder is 112. So like quotient 7, remainder 112. After you've done this, essentially what you do is you do another division, but this time it is this number, it is this 175 that you divide, and you divide it by the previous remainder. You divide by 117. So once again, you're going to have a quotient and a remainder. I mean, this process is a bit boring, and you just have to like numerically do it. You do 175 divided by 1223 and 175 modulus 112. And you get quotient of 1, remainder of 63. You get quotient of 1, remainder of 63. And you repeat. You take this value, which was the previous divisor, and now you divide that by the previous remainder. You repeat this process. So let's repeat this process. 112, 63. This is 112, 63. So we get quotient of 1, remainder of 49. You repeat this thing, so 63 is like 63 divided by 49. I mean, this is just boring mathematics. Times 1 plus 14. You repeat this with this. So 49 you divide by 14. 49 you divide by 14. 3 plus 7. Okay. Now you divide 14 by 7. So 14 you do 7 times 2 plus 0. So the first step, you just keep doing this kind of divisions. You take your calculator and you do these divisions until you find a remainder of 0. At this point, you stop and you say, okay, I have found a remainder of 0. We don't care about this last equation, this 14. We will start essentially from these other ones. So keep dividing until you find a remainder of 0. Then consider the second to last equation. Second to last equation, which in our case is this thing. So essentially, in this equation, we have found the GCD of our numbers, which is 7 actually. The GCD between 1237 and 175 is 7. The idea now is, remember what we want here at the start. We want to express A and B, our initial numbers, as like a multiplication and sum equal to the GCD. So we want this equality. Okay, now we have found our GCD and we can express, like what we can do here essentially is we can try to express, like we can say, okay, 49 times 1 plus 14 times minus 3 is equal to 7. It's like I'm close to what I want, but the problem is that I don't have A and B. I have like this 49 and 14, which appear during the computation. So now there is like a super boring process in which you essentially you go backwards and you substitute each equation so that at the end you get like an identity of the form where you have like here 1337 times something we don't know, here plus 175 times something else we don't know, equals to 7. And to get those x and y, you have to essentially do this. So now we will see how to get this x and y. So we have to express each equation here in terms of remainder equal to the to the rest. So like 7 is equal to 14 times 1 plus 49 times 1 plus 14 times minus 3. Then we do the same with the previous one. We express it like 14 is equal to 63 times 1. And then, of course, we have to put the 49 to the other side. Here, remember, here, look how I write 49 times minus 1. I'm not writing minus 49 because I'm not, let's say, resolving those multiplication. I'm keeping them as multiples of 49, 63 of those numbers that appear during this computation. And I do this for every line, like I do 49 equals to, so this kind of thing, 2 times 1 plus 63 times minus 1, and then I get 63 equals to 105. I mean, this is like row computations, pretty boring. 112 times minus 1, and then I do 112, which is 1337 times 1 plus 175 times minus 7. Okay, now what I can do is I can start from the first equation, this thing, and I can start to substitute. Like, for example, here I have 14 times minus 3. But now I can express 14 in terms of 63 and 49. So here I do this kind of thing. I do the first term, I keep it as it is. Then this 14, I substitute with whatever I had previously, and I get this thing. And here, I mean, this is the confusion part, because this is like you have to be careful. I mean, in the exam, it's going to be super easy. So this just to understand the computation. And this is why I also did not resolve the multiplication, because now I can do this. I can just group like magnitude terms. So here I have 49 times 1 plus. Here I have 63 times 1, but then this is times minus 3, because this is a parenthesis. That like, so essentially I have 63 times minus 3, because I just multiply the number in the parenthesis. And then I have 49 times minus 1, everything times minus 3. So I have plus 49 times 3. So here I have done minus 1 times minus 3. And here I can group together the 49s. So I have 49 times 4 plus 63 times minus 3. And I mean, yeah, this is like pain in the ass, and you just have to work through it. So this is times 4 plus 63 times minus 3. And here is like everything in like parentheses, I think. Wait a sec, I lost myself in the parentheses. Okay, let's do it again. So 49, I put this expression for 49, and here has to be times 4, plus 63 times minus 3. So I have 112 times 1 times 4, so that's times 4, plus 63 times 1 times minus 1 times 4, so that's 63 times minus 4, plus 63 times minus 3. I rearrange like the 112, I just write it, and I combine together the 63. So that's like minus 7, because it's minus 4 plus minus 3. Now I rewrite the 63. We are almost there too. So it's like almost done. This suffering. So we write this times minus 7. So once again, I rewrite this first part, and this second part I do 175 times minus times 1 times minus 7, that's minus 7, plus 112 times minus 1 times minus 7, that's 7. And then I have 4 plus 7, that's 11. So 112 times 11. Oh, and at each step, something that I have not done, you can actually check if you have made any mistake, because they all have to be equal to 7. So let's see if I made a mistake. Okay, this is equal to 7. I did not make any mistake. If at some point you go outside 7, you rearrange terms wrongly, and you did some like computation badly, we are essentially there, because now look at what we have. So we have 112 times something plus 175 times something else, which is equal to 7. The only thing we need to substitute now is the 112 with the 1337 plus this thing. So we do this plus this thing. So what do we get? Okay, so 1137 times 1. Oh, sorry, because I forgot here there is a times 11. Times 11, so 1137 times 11 plus 175 times minus 77 plus 175 times minus 7. So let's see if I... Okay, this is still 7. So this is 11, and this is 77 plus 7, 84, minus 84. Okay, let's see if this is 7. I hope so. 87. After all this like suffering, what we have found is, okay, we do 157 times 11 plus 175 times minus 84. This is equal to 7, which is equal to the GCD between 157 and 175. So this algorithm allows us to do this kind of computation and to express this kind of identities where you have your first number of the GCD times another plus the second number times another equal to the GCD. Now, why does this actually matter with respect to RSA? Because as we said, in RSA, once we have this configuration, we want to compute the private key. And so like the private key is done by solving this equation. So we have to find a value D such that d times q, I mean, this is not d times q, but it's d times e minus phi of n times q is equal to 1. And this is also the GCD between e and phi of n. It means that this equation is like finding two coefficients that, like, when you multiply e and phi of n, you get essentially 1. So this we could write this as e times d plus phi of n times minus q equal to GCD of e and phi of n. So this is like if we are able to, like, with our algorithm, we find that this d and this also minus q, but with the minus q, we don't really care. We care about the d. So essentially, for like for reviewing, so compute. So we have these parameters. Okay. Compute private key d. We execute the extended Euclidean algorithm on the values e and phi of n to find x and y such that e times x plus phi of n times y is equal to the GCD of e and phi of n, which is equal to 1. This last part is equal to 1 by construction. We know that because we choose e such that this is true. Once we have found such x and y, the private key is d equal to x. So the private key is the coefficient that we multiply e with to obtain this identity. So like we execute our algorithm, but we only care about the coefficient for the e, not for the phi of n. And this is our private key. And I mean, this is like computationally boring for us humans to do, but it's actually really efficient as a complexity, as a process. And there is like a code. Like I just suggest to try with small numbers. You don't need to like do big numbers. But the important thing is that you understand like the structure of this computation, so that you can do it with like in these notes. I think that like at the end I give some few like things in the context of RSA. Like I don't know, with this configuration, compute with this message, compute the ciphertext using the square multiply, or with another configuration, compute the private key, which is the value d that makes this equation true. So like these are like the main two things, and you can find in the resources, like in the code zip, you just download it, and you find these 3 files that allow you to test your understanding of these things, because you have the square multiply that you call with x, y, and n, so you can test. Like for example, the exercise required to compute the ciphertext when the plaintext was 1337, so that's the base. So the base is 1337. The exponent in this configuration is e, which is 13. The base is 1457. 1457. So the exponent is 994, but of course you have to write the algorithm by hand, so you can test like if you did it correctly. And for example, for this order, find the value, the private key d. What do? Well, you use the extended GCD, and the extended GCD requires two values, a and b. You put them a and b, and it gives you the expression such that you have a times x plus b times y equal to the GCD of a and b. So like you can do, for example, in this test, we want to compute the private key with this configuration. So e is 3, okay? So here we have to put 3. Phi of n is, well, n is p times q, where p is 2333. So like if I have p 2333, q is equal to 275. It means that phi of n is equal to p minus 1 times q minus 1, 232 times 276 So this is like, let's do it in Python. Python should 2 times should 56. So this is the phi of n. And so you can solve this by calling the extended algorithm with. So you do extended GCD. E is the the first number, which has to be 3. Just to be 3, and the other numbers to be this order. And you get this thing, so you get that you have this equation, and the private key is the number that multiplies the E. So it's this minus thingy. Of course, we are working modulus, so you can just get the relative version modulus, and to get the relative version modulus, you can do like the modulus. I think it's like this private key is modulus phi of n. So this, I mean, you can just do the minus modulus. This is the positive version of the same number. And indeed, let's test it. If I do 3 times this, and I reduce everything modulus the phi, I should get 1. If I get 1, it means that with this, I can decrypt messages. If I do like a message to the exponent tree and I reduce modulo n, and in this configuration is this thing, I get back something. If I take this something and I elevate to the private key and I reduce modulo n, I should get 1337. So these are like invertible processes. So yeah, I mean, this is essentially it. It's like boring, mathematical processes. The main thing to understand is square and multiply, the first one, you write the binary representation, all the ingredients, you stop until you find a power that is higher than what you need to express the exponent, and then you put everything together. So it's like 3 steps. And I mean, as I said, in the midterm, there are going to be small numbers, so this step is going to be pretty fast. You will have at most like 5 to 10. 10 is really a lot, actually. This is for the first. For the second, it is a bit more involved in the sense that you take your 2 numbers, because you are given 2 numbers, you start by dividing them in a cascading manner. So first you divide A with B, then you divide B with the remainder of the previous division, then you divide this thing with the remainder of the previous division, and you keep going. You keep going like this until you find 0. Then once you find 0, you go to the previous equation, you express everything in terms of the remainders, and you start substituting starting from the top. So I really suggest like going, you go down, then you go up, and then you say, okay, if 7 was like the last one, I'm going to put it as the first. You keep substituting, and then when you do this substitution, go in the order they appear in the list, meaning that here I had to substitute both 49 and 14, but the first one I substituted was 14 because it was the next in the list. So this way you can have like an ordered process. Like here, I substituted 49, not 63, because 49 was the next one in the list. And this is like you keep going at the end after like this substitution. And like now, this was pretty like you had to be careful. But when you do the substitution, always write the numbers in the form. Like one of the remainders times something in like parentheses. So you don't mix out and you know the factors. Because when you substitute, you can always group them together. And this simplifies the computation. At the end, you will arrive at something that is the first value you started with, the A, times x, plus the second value you started with times another y. And at each step of this substitution, you can do some error checking because it always has to be equal to the GCD. When you are computing the inverse of like the private key of RSA, this GCD is always 1. So like all these computations, they have to be equal to 1. And this is like this is pretty much the idea. So now I think that with respect to the lecture material we are done, here are the like midterms exams. You can check them out if you want. And just to like some transparency with the like what I require during the midterm. I mean, I can talk with myself, not of course with respect to professor. My questions, the open questions, which were two. So like the first one was about the differences between cryptographically secure generators and not cryptographically secure. And here the main idea was predictability. I mean, if you mention that the secure one had to be unpredictable, you would get like at least like a 6. Because that's like, I mean, what I require is a general understanding of the different concepts. Maybe you don't have to like go all in the details. I don't care about that, but just being aware that if you use like a Python random, that could be predictable and it could be like dangerous. So this is like for the first question. Of course, to the ones who've written the two properties more formally, I've put like a higher grade. But I mean, to be honest, I don't really believe in like too much about grades. But at the same time, of course, you have to understand if someone has studied. So like I've come up with 4 mainly types of answer, which is no answer. And I mean, it's okay. You just have to study. And here I put the link to the material. I mean, I guess a thing that could be problematic was like, okay, I have all this kind of stuff. Which are the most important things that I could ask about? And like in this case, in this lecture, we've seen 2 algorithms, so you just have to execute those algorithms. So I guess I can understand that maybe you have a lot of material, so you don't know which question I will ask. But in general, it's about general understanding of the topics. So like if you have like 1 hour and a half about generators and the point of the lecture is showing that you cannot simply use any generator, you have to understand how it is implemented and what kind of properties does it offer. Like at least a general understanding between those kind of things. Like and then like there are some people who answered about who answered by defining what is a cryptographically secure hash function. And I mean the answer was correct in itself, but at the same time it's like it is an answer to a different question. And I mean I guess everyone has its own grading method, but I believe that if I ask you something at least like I prefer actually no answer than an answer to a totally different question. And so yeah, especially because in cryptography, I have seen people confuse like encryption with hashing. They are different concepts, and they need to be, differentiated in the real world. Otherwise, it's really a problem. Like when some like data gets breached, it's also because people do it wrong, and it could be like really problematic. So it has to be like you have to be careful. Then like there are the two final answer, which is answer without enough detail, which is it's still good because it means that you have understood the like the idea. Maybe you need to study a little bit more. I think that with this respect, it is up to you. I mean, if you want to truly understand or not, like to pass the exam, it's like whatever. But at least you know where to go essentially. And then there are like answers with enough details, which is good. And with respect to like the first answer was like pretty general. I mean, simply they mention about predictability. And those who mention the two properties, which are like the next bit test and the state compromise extension, I mean, that's good. It means you studied. The second answer, the second question of mine was about the LCG. So like here, a lot of people did not answer at all. But I mean, like the idea, I just wanted to like to write out the equation, and then the the idea was that, I mean, the problems of unsecure generators is that if you observe the output, this gives an attacker an edge. So it was the mentioning of that you attack it by observing outputs. Knowing this means that when you implement such generators, maybe you ask yourself, can an attacker see a direct output? Is this problematic for my generator? Something like that. And for like the particular equation, like it was like for the extra to get upgrade, but the most important aspect was like defining the equation just to understand that like some of these generators are pretty simple mathematically. They're not that complex. And yeah, and this about observing outputs. And that's it. I mean, you can check the exams if you want. I mean, I don't know if like you can understand to which class you belong. I guess it's like it's different. So maybe you can check them and you can ask me, because if you can ask me, I can tell you like exactly what kind of things I've seen in your answer. And this is like essentially it for this lecture.